We can move to our last speaker. We have Stephen Peterson, a postdoc at the University of Washington in the lab of Brenton and Rao, and he will be presenting us his work on transferring generalized neural decoders across participants and recording modalities. So please, Stephen, take it away. We cannot hear you, sorry.
No, sorry about that. Thank you.
No.
All right, so yeah, I will be talking about creating generalized, robust neural decoders. And so the motivation for this is brain-computer interfaces like this, and also similar ones like this, where you sort of take neural data that you record and interpret it in a way to control some sort of device. And there's a lot of really cool things you can do with that, but there are some limitations in terms of you need a lot of training data that can take a long time to get. And you also may need to recalibrate frequently because the data you record is non-stationary. So the problem is that we have these great decoders that we want to train, but the amount of training data we have is really limited and can be very time-consuming to obtain. So a solution to this is, instead of trying to get a lot of data from one participant, is to get a little bit of data from a lot of participants, basically. And then you can create this decoder that takes in all of that data and finds some representation that works across all those participants. But it does have to be robust to differences across participants. And I'll get to that in a second. So the input data I'll be talking about here are neural population recordings. So thousands of neurons, tens of thousands of neurons. So I'll be talking about ECoG, which is electrodes on the surface of the cortex underneath the skull, and scalp electroencephalography, or EEG. And so ECoG has a really nice high signal to noise ratio. However, it's invasive, and so it requires surgery. So we only look at this usually with clinical patients. Whereas ECoG is really commonly used in research. However, it's very much prone to artifacts because it's above the skull and can move a lot. So back to what I was talking about with the generalized decoding and how we can create these inter-participant differences. One of the things that can differ from one person to the next is the frequency content of the signal of interest. So here I'm showing a spectrogram, which is basically in the frequency domain of your signal, average across 12 participants. So it's very similar if you're doing like a Fourier transform. In this case, it's wavelets. So the x-axis here is in time, where 0 is when the participants move their contralateral arm, and frequency is on the y-axis, and then the color scaling is in decibels and indicates the magnitude of the spectral power of the signal. Basically, what I want you to take away here is that there's these two very distinct bands of activity, this low frequency power decrease and this high frequency power increase. But if you look across participants, you actually see that there's these differences. This pattern is not conserved across all participants. So what you really like to do is figure out what features are robust and consistent across all participants when you're creating a multi-participant decoder. Additionally, particularly for ECoG, because it's clinically motivated, the electrodes are placed based on clinical need, and there's no standardized placement. So this is showing 4 ECoG participants colored differently. And you can see that there's not necessarily a great way to always align electrodes among participants. That's another challenge that we want to address. So the main idea is take data from multiple participants, train a generalized decoder, and then also we can take just a little bit of data from some participant we've never seen and fine-tune that generalized model using much less data than we had before. All right, so first I'll talk about the generalized decoder. And so similar to what Sebastian talked about, I'm using a deep neural network, in this case, convolutional neural network, because it generates data-driven features. In this case, I'm looking at stuff applied directly to the neural data in question. So for this, we used ECoG. This is a model created by Lawhorn et al. In Journal of Neural Engineering. It's a really nice paper if you're interested. Basically, it takes the EEG data segmented on the left, runs it through this decoder, and then outputs some decoded behavioral state, decodes your behavioral states. One of the reasons I really like this is the temporal and depthwise convolutions at the beginning are very analogous to a data-driven bandpass filter and a data-driven spatial filter, respectively. So to me, that's very understandable, and it's a very common pre-processing method when you do neural decoding. So one of the downsides of this method is so it can sort of sort out differences in frequency content, but it does it all in the time domain. And one of common ways to analyze neural data, at least from ECoG and EEG, is to look at it in the spectral domain, similar to that spectrogram I showed before. So to do this, I inserted a Hilbert transform here after the temporal convolution. And Hilbert transform is very similar to wavelet transform. It's like a Fourier transform, but it can handle data as that changes. So like here, you can see that the power of the signal changes over time, and the Hilbert transform on the bottom here actually picks that up and changes with it, which is good for non-stationary signals. This is also, with a temporal convolution, very similar to data-driven filter Hilbert method, which is nice. So that sort of allows for that. But the downside still is that this is made for EEG data, so the electrodes are assumed to be consistent, which is not the case for something like ECoG. So to get around that, we pre-computed these weight matrices between the electrodes, which vary across participants, and common predefined brain regions that are the same across all participants. And so you have to just pre-compute these, but you can insert them into the model and do a matrix multiplication partway through the decoder itself. And what that means is everything before the matrix multiplication step differs across participants, but everything after the multiplication step is on these same, same points across all participants. And so it really gives the decoder a chance to do a good job in decoding. So that's how we created the decoder. And now I'll talk about how we actually tested this and how it performs in practice. And so for this, we tested on real data. We looked at 12 participants who had ECoG, and this is part of our long-term clinical naturalistic monitoring data set that we have. That's part of the preprint in the chat. Additionally, we also looked at EEG from 15 participants, and this is from a paper by Offner et al. And +1. And for both of these cases, we were looking at decoding between rest, where they're not moving their arm, and move, where they're just sort of doing some sort of roughly elbow flexion. That's what they're doing in EEG. In ECoG, most of the movements they do look very similar to that. So it's just two-state classification. And in terms of experimental design, what we did was we took 11 of those 12 ECoG participants and trained/validated on those. And then we tested on withheld data from a withheld, from that 12th ECoG participant, and that's what we call the same modality condition. And then we also tested on the unseen EEG participants, and that's what we call the unseen modality condition. And of course, we also randomized, did a bunch of models where we randomized, which participants were training, validation, and test set, and did that 36 times and looked at the results to ensure or reduce any bias in how we did things. So first, for the same modality conditions, so this is going from ECoG to testing ECoG participants. So these are the accuracies we have on the withheld participants. So test accuracy is on the y-axis here. And then random chance is at 0.5. And so what you can see is HTNet does much better, significantly better than these other three decoders. So EEGNet, random forest, and also minimum distance. It's really important to note here that because this is trained across multiple ECoG participants, I actually had to include that projection step onto common brain regions, because otherwise this would just not work at all. There would be no way to align these things very well. So the only difference between HTNet and EEGNet is that Hilbert transform. And you can also see across ECoG participants, when they were the test participant, in general, HTNet seems to do much better than the other three methods. And then looking at unseen modality decoding, this is originally, when I tried this, I did not expect it to work very well at all. And for 3 out of the 4 decoders, it kind of works as you'd expect. The scaling is different in some ways. The noise that you get is very different. And so the decoder can't really generalize without having seen anything. But in HTNet's case, it actually can. And this is mostly due to the fact that it looks in the spectral domain, and you can do relative power metrics that actually are very robust across at least EEG and ECoG modalities. And this is also very consistent across different EEG participants. Okay, so talked about how we can train those decoders, and now I'll talk about fine-tuning them. And so this involves taking a pre-trained model, so any of the models I just showed you, and then taking a little bit of data from that withheld participant that we're testing on, and then training on it a little bit to fine-tune it a little bit more towards that participant, and then testing again. And so this is work that another grad student in the lab, Zoe, has helped out a lot with and worked really hard to do. And so when we fine-tune in the same modality condition, we're taking the pre-trained model from before and then training a little bit on that withheld participant and testing on the same data as before. And what you can see here is that even with just a few training events, so like up here, you get this really quick boost in performance that's consistent across participants. And so when this pink line here shows the performance of randomly initialized decoder, and then these other ones are the fine-tuned ones. You can see that initially, as you might expect, randomly initialized decoders don't do so well, and over time they do pretty well. But even that performance you gain here with over 1,000 events is very similar to what you gain with a fine-tuned model with very few events. And you can also see something very similar for the unseen modality decoder. So yeah, so just to wrap up, showed you how we built this generalized decoder for neural decoding in both ECoG and EEG. Showed you how we can test that and how it actually outperforms other comparable decoders. And that you can also fine-tune this model, these pre-trained models, and not have to use too many fine-tuning events to get really good performance for each participant. And so there is a preprint that should hopefully be coming out within a week or so. Yeah. And I'd also like to acknowledge all the help from the Brunton lab and Raj Rao's lab, who are both my co-advisors, along with all the clinical staff at Harborview who helped collect the data and work with the data, along with our funding sources. And I also want to thank you all for paying attention and listening. And if you have any questions, I'd be happy to take them. Thank you.
Thank you very much. Really, really interesting. I'm quite impressed. Honestly, I was not coming from fMRI and being so focused on topography most of the time. The idea of trying to go across participants that have a different coverage, just as an idea, scared me. So maybe could you elaborate a bit? It probably was already in your graph with the individual participant performance, but how much does the decoder performance vary as a measure of how similar is the coverage across participants in the end?
Yes, that's a great question. So I didn't show it, but basically we also did test that to see how much the training participants overlap with the test participant. Mm-hmm. And you can actually see that the decoder does a lot worse when there's not as much overlap. As you might expect, if you're not training on the area that you're interested in, doesn't necessarily generalize as well. But we found our decoder, when things overlap really well, just performs much better than these other decoders that we were looking at.
Right. And okay, so we see another question, and I should let someone else ask as well. So Joelie is asking, can you elaborate on why you choose to use a pre-computed projection matrix to account for different recording locations versus learning that end-to-end?
Yes. So in some ways, we had actually tried to do sort of a learning end-to-end. We had tried to do some matrix completion with this before, and it just did not work very well at all. That's basically the short answer. I think there might be a way to make it work. The nice thing about this is it uses information that we already have available and that we can get pretty early on, and sort of just constrains things so we don't have to learn as many parameters. It should take less time to train and be most likely a little more stable.
I see. Okay, we have another question from Karen Jerby. Is asking, was the random forest classification used with spectral amplitudes from the Hilbert transformed as features? This is probably needed for a fair comparison with your model.
Yeah, so that's a great question. The stuff I was showing here was using the time domain. I've looked at it with the Hilbert transform as well, and it, the performance, as you might expect, does improve. One of the things I was trying to stay away from with not doing the Hilbert transform in advance is you sort of need to know what frequency bands are of interest before you do it. And I think that's one of the advantages of the HTNet method is you don't really necessarily need to know anything about your data, at least about the specific bands in and of itself, because it can kind of learn those. But that is a very fair point. If you do know what you're doing, what you're looking for in advance, you don't necessarily have to do this.
Sounds great. I think we're out of time, but thank you very much to all three our speakers.